chat. Okay, so let's get going. So what is linear algebra? So in the most concrete form, linear algebra is the study of systems of linear equations, which are the equations of this form, equations like this, right? So here you see it's a system of three equations of variables x, y, and z, right? And then the goal is to find the solution of this system of equations, which is of course a familiar task for you. I think you've done this in high school. So we'll spend first few videos, first few lectures on the concrete manipulation of equations using new methods, using matrices or using linear algebra. So here's a hint of what's about to come. So systems of linear equations, they have a geometric meaning. So equations from the previous slide, you can, so since it's x, y, and z, you can draw them in three-dimensional space, right? And then each of those equations will carve a plane inside three-dimensional Euclidean space. And then what we're looking here is for the intersection of all those three planes. And then in this case, this point over here will be the solution of this equation. So the region where each of the equations is satisfied is a plane, and then simultaneous solution of all the equations is where all the planes intersect. Yeah, so feel free to pause or ask questions at any time. Good. And then yeah, you can do it, say, in computer graphics or computer vision. More abstractly, it's the study of transformations of spaces which carry lines to lines, right? So if you have a line in space or anywhere, its transformation will be also a line. So it can be oriented differently. It can go in a different direction, but it cannot be anything like this, right? It cannot be a wiggly line like that. Now, what is a space? What is a line? So those questions need to be, and what is the transformation? We will answer those questions in this course and many others. But today we're not going to go there. We just look at some examples. So first, let's study the many examples of the. Let's look at some examples. The more abstract perspective is worth the effort. So many phenomena in linear algebra. So many phenomena in nature are linear in either an abstract sense or in some approximation. For example, Schrödinger equation for quantum mechanical particle, right? It's an example of a differential equation, and we'll talk about this kind of equations later in the course for the last 3 weeks, right? Okay, has anybody seen Schrödinger equation before? Raise of hands. Nicole, good. Or yes, others, 3 or 4 people. Yeah. So, okay. So it represents the its solution is psi of x and t is the wave function, right? Or it's the state of quantum mechanical system, which is described by this differential equation, right? So there's the derivatives in time, and there are derivatives in space. So this nabla squared is the Laplacian, right? So the space of functions is all of those psi's of x of t also in the presence of initial conditions and boundary conditions which satisfy this equation. And linear transformations are partial differential operators, right? So you will have so think of this operator IH d over dt, this time derivative, as a linear transformation. It might sound a bit bizarre at the moment, but there's actually a way to think of a derivative as a linear transformation. Jessica, yes, I'll post slides too. Yeah, absolutely. So all materials that I have will be absolutely available as soon as possible. And also, so basically the left-hand side is a linear transformation on the wave function. The right-hand side is a linear transformation on the wave function. Okay. So an equation is linear, right? Gori, you still have a question, or you just holding the hand from the previous time? Also, Sahil. Okay, never mind. And then so by the end of the class, we'll find that the Schrodinger's equation, this one, will look no worse than this one. So the sort of art and this beauty of linear algebra is that it allows you to develop a framework which treats many sort of all linear systems are treated in the same way. And this sort of the goal of this course is to develop the machinery which would allow us to do that. Yeah, of course, like this thing looks easier than that one, and it is, right? And it is, but it's just they belong to the same class of linear sort of they can be studied by methods of linear algebra. Now, some of the phenomena are approximately linear, right? So many sort of physics experiments, right? You would measure some data points, and then you would approximate them with a curve. And often this curve is a linear function. So discovering such statistical linearities play a major role in experimental sciences and so on. And then another example, well, one of them is for calculus, right? So you would take like the tangent line to a differentiable function, right? And then you said is a linear function, or tangent plane to a surface of the graph of the function is 3-dimensional. It's a linearization of what's going on in the neighborhood of this point. And then, yeah, so in linear algebra, we will discuss in the differentials. It's sort of it's very natural home for linear algebra in calculus, especially in higher dimensions. Right? So often you cannot draw a picture, but you can write a vector and a matrix, and then you can treat the problem using this abstract notation. Okay, so what we're going to learn, concrete procedures for manipulating linear equations, then abstract notions, which stand behind linearity. And then, yeah, so we'll talk about some applications and real world phenomena. So one of them I just showed you, the quantum mechanics, the Schrödinger equation, which describes the quantum mechanical state, how it evolves in time and depends on space. It will be a lot of work. Yeah, so, but you signed up for this yourself, right? So, you know, in summer, things are pretty intense. And I'll try to help you as much as I can. So that's why I sort of want to have as many discussions as possible. So think of it as 20, 30 hours per week, like grand total. But I mean, of course, if you are, you know, you don't have to spend that much if you can do it faster. Yeah, so this is just a non-scientific advice. You can ignore it if you like. But if you work hard, you'll leave the class equipped with a lot of conceptual knowledge, which sort of, I mean, application of linear algebra goes across the board, right? No matter where you go, it will be an essential part of pretty much every subject. Okay, so let's get started. Any questions about the intro? Okay, so we'll talk about linear equations. Example, consider equation x plus 2y plus 3z is equal to 6. It is linear in x, y, and z. Well, let's give a definition what it is, what it does mean to be a linear. An equation of variables x1, x2, etc., xn is linear if it can be put in the following form. So it's a1 times x1 plus a2 times x2 plus etc. plus an times xn is equal to b, where, and here's an important point, the coefficients a1, a2, and an and b do not depend on any of those variables x1 through xn. So usually a and b are just explicit real or complex numbers. Are you familiar with complex numbers? Who is not familiar with complex numbers yet? Raise your hands if there is a person. We will need some of the complex numbers later when we'll talk about eigenvalues, but not today. Okay. Now let's give a sort of non-example, which is stresses on the fact that these coefficients must not depend on the must not depend on the variables. Consider equation x cubed equals 6. So obviously it is not linear in x, but you might write it as, x squared times x equals 6 and pretend that this is the coefficient. But you would be wrong because this coefficient depends on x, right? So this kind of comment here is very important. Now, another example, sort of example, non-example, the equation xy equals 1 is linear in x and it's linear in y. So if you think of x as an independent variable and y as a parameter, it's linear in x or vice versa, but it's not linear in both x and y, right? Instead, it's quadratic in x and y. Okay, so how about try it yourself? Is this equation linear? X1 equals 5? You can respond either verbally or in chat. Yes. How about this? Good, it's linear. How about this one? Yeah. How about this one? Right, so S is just a parameter here because the question was, is it linear in these guys? Okay, how about that one? No, right, because of the right-hand side, so it's not linear. This one? Okay, okay, Queenie, why is it not linear? Or Jessica, so
it's not linear because it's making use of x1, x2, which are like part of the.
Right, so I mean, the left-hand side looks kind of linear. Okay, so some folks said yes. What about G Kang? What do you think? You said yes to the last one, or what?
I thought you could rearrange it, multiplying by both sides with x2 and it'll become linear, but I'm not sure.
Exactly, of course. So, but there's a condition, right? So that forbids x2 to be 0. Exactly. So you can just multiply by the denominator, and if it's okay, I mean, if you're, in your problem, you can somehow exclude the area that sort of exclude the domain when x2 is equal to 0, then it behaves like a linear equation, right? It's x1 minus 4x2 is equal to 0. But if not, then it's not true. So it's a little bit tricky. Does that make sense, guys? Yeah, okay. So it's linear everywhere where x2 is not equal to 0, and it's non-linear when x2 is equal to yeah. Okay. Now, so far we talked about single equation. Now let's talk about system of equations. A system of linear equations in x1 through xn is a finite collection of linear equations in these variables. So, and we can write it sort of in this lined up form, right? So now we need, for the coefficients, we need double index, right? So a11, a12, and so on. So first equation is this: a11 x1 plus a12 x2 plus etc. plus a1n xn is equal to b1 and m minus 1 others. So there are m equations for n unknowns. Yeah, so it's, and then m and n, they are independent, right? You are free to consider any positive integers n and n. Okay. Now let's get back to this first equation that I showed you in the first slide, on one of the first slides. So this is the we have 3 equations for 3 variables. Well, here they're called x, y, and z. Here's an example of 2 equations and 3 unknowns. Unknown is or variable is the same thing, right? So there's that. And here's an example of 2 equations and 1 unknown. Is there anything odd about the last one? Yeah, so there are 1 unknown, but I wrote down 2 equations, right? So I can do that if I want to. Okay, so we'll get back to this equation, to these 2 examples later. Okay. Now, let's talk about solutions. We want to find space of solutions, all possible solutions of the linear equations. That's what linear algebra is about. So by definition, the set of solutions to a system of linear equations in x1 to xn is the set of all tuples of numbers s1 to sn, such that substituting si's for xi's gives an identity. Right? That's the definition. Examples. Okay, so this equation x1 equals 5 has a solution set 5. Right? So it's sort of more or less a tautology. If you plug in x equals 5, it works. System x1 equals 2 and x1 plus x2 equals 7 has set of solutions 2, 5, right? So if 2 works here, 2 plus 5 is equal to 7, it works there. Now, but if you write this, the equation system of equations x1 equals 2 and x1 equals 7, it has empty solution set, right? So because these two equations, they contradict each other. Now the system x1 plus x2 equals 0 has the solution set s minus s, where s takes any value, real or complex, right? So if you're solving a solution for complex numbers, s can be any complex number. Any questions here? A system of another definition about consistency and inconsistency of solutions. A system of linear equations is called consistent if it has solutions and inconsistent otherwise. So we saw examples on the previous slide. Now, in all of the examples, we have either none, one, or infinitely many solutions. And then we will show then this is always the case in linear algebra. So it's either none or unique solution, or there are infinitely many solutions. Sort of, if you like, this has something to do with the fact that lines or planes, they can either, be parallel, right? They can intersect in one point, or they can sort of coincide, right? So one on top of another, right? So in this case, so here we have no solutions, here we have single solution, and here we have infinitely many. So the reason why, for example, you cannot have two is because, so say you have some high degree curve like this, and that they can intersect more than one time, but those are not those things are not studied in linear algebra. So this is the intuition behind that fact. Okay, so how about this system? Is it consistent or not?
Inconsistent.
Inconsistent, of course, right? So the space of solutions is empty set, and if you try to draw this in a previous, so think of these equations as equations for lines in R2 in two-dimensional space. So there will be just two parallel lines, x equals 1 and x equals 2. How about this one? Is it consistent? Is it consistent, and how many solutions does it have?
Consistent and infinity.
Infinity. That's right. Yeah. So indeed, so there's like there are two conditions for three unknowns. So you can see here that one of them is free. So you can pick a number s, any number s, and then this tuple, this triple of solutions, you can check that they satisfy the equation, right? So you can substitute x plus y equals 1 on the first equation, and you'll have that y plus z, because x plus y is equal to 1, so then it will be z plus 1 equals 0. So z is minus 1, and then instead of x, you can plug in any variable. Question: what is the significance of an inconsistent system? Does it mean no solutions? Yes. So Cindy, by definition, it is here. So consistent simply means it has no solutions. Yeah, it's just a different word. Okay. Other questions? Good. So this one has infinitely many solutions. Okay, so can somebody tell us what's the geometric is the okay? Let's not go there. Yeah, let's move on. We'll talk about geometry later. Okay, now let's do together this one. So the three equations, which look sort of more sort of less sparse than before. Three equations, three unknowns. Okay, so of course, if you use your methods from high school, well, you know what to do, right? So you take, say, first sort of middle equation over here, right? And then you solve it for x, right? That's also easy to do. And then you substitute it back to the other two equations. Yeah, so I think most of you would pick the second equation because, like, when you express x, it looks nice and with many pluses, right? So there's a certain choice you make once you do the this elimination procedure, and then the other two equation will become the other two equations will become, well, as I wrote here, right? And now you can simplify. You can combine the common terms. Just going to show this again, but I'm sure you understand. Okay, Yang Ji found the solutions. Great. So 1, 1, 1, 1, right? So 1, 1, 1. You can check that. Okay, let's see if Yang Ji is correct. So you plug in 1, 1, 1. So that's 6. That's 1. Yeah, that works. So let's get. I'm glad that it's easy for you, and it's supposed to. You simplify them, and then you need to do elimination again because you have two equations and two unknowns. So if you use the first equation, you solve it for z. Have this fractional coefficients. Okay, so yeah, if you have to leave, please go so that you can watch the recording later. Yeah, so I'll post recording and I'll post the slides, so everything will be available. And then substitute this into the second equation to find, well, this one, or you can solve it for y, and you'll see that y is equal to 1. So if y is equal to 1, then you substitute it back, right? So kind of you found the first unknown variable, y equals 1. Then you substitute it here, for z, you find that z is equal to 1. And then you find that x is equal to 1. So if you like, our algorithm, so you had sort of two parts of the solution. So first we eliminated variables until we got to the to 1. So which one equation and one unknown, which is this one here, right? And once we found the solution, we substitute for this variable, we substituted it back to the other equations in reverse order, right? So here we went. So first, so we solved for y, right? Excuse me. So yeah. So first, let's rewind it back, right? So we first got rid of x, then we got rid of z. And we find the equation for y. We solved it for y. And then we're doing the substitution backwards in the reverse order. Y goes into the equation for z, and then z goes into the equation for x. Z and y goes into the equation for x. So keep that in mind. We'll be talking about the matrices. Okay, so that worked, but it was, not fun. So first of all, 3 equations and 3 unknowns is not a big deal. But what if you have 100 or 1,000? In fact, real life applications like those modeling that people are doing on the computers, I mean, it involves many equations, sometimes thousands or hundreds of thousands. So of course, you're not going to do the substitutions. Just it will eat up all your computer power. Now, so let's clean this up a bit. So when we transform this system here into this one, right? So if you have so here, see the first and the third equations, they don't contain x in them, right? So we solved it for x, second equation for x, and we substituted it in the first equation and in the third equation. And then, yeah, so that's what we did. Now, instead, let's just rephrase this. We're gonna, of course, we're doing the same thing. I'm just gonna present it in a different way. We will be subtracting the second equation from the first, right? So just multiply this by -1 and then add it to the first equation, and twice the second equation from the third. So you multiply this by -2 and add it to the third equation. you can see that you'll get the system that we see on the screen right now. Yep, I'm sure you also have seen this before. Now, again, and then when we did substitutions for y, instead we can transform into, so on the next step, right, when we do the solution for y, we start from this equation, and then what we're doing, we're subtracting the first equation from the third. So you have 2z here and 2z here, so it's tempting to cancel them out, right? So you multiply the first equation by -1 and add it to the third equation. And that's how we end up with 2y equals 2. Okay, and then we can simplify further, divide the last equation by 2, have this. So, and then we didn't do anything with the first two equations. So now we can add multiples of the bottom equation to the first two. So we multiply the last equation by -3 and add it to first equation that gives us 2z equals 2. And then we just add the second and third, and it gives us x plus z is equal to 2. Right? So we get that. I know it may sound a bit ridiculous to keep doing it this way, but that's what the linear algebra, that's what the elimination procedure is about, right? Let's sort of do it till the end, the way we're doing it. Okay, and then we divide by 2 the first equation from here. Get this, z equals 1, x plus z equals 2, y equals 1. And finally, we subtract the top equation from the middle one, right? So now we're sort of subtracting this one here. So multiply by -1 and add with the second equation. So we get 1, 1, 1, 1 is the space of solutions, right? So yeah. So you see, it did not require any manual substitution and division. So, and moreover, we did not do any, we did not deal with any rational coefficients here, right? So if you remember what the first sort of school version of the solution, you would divide by 2 or by 5, and those it's very easy to make a mistake when you multiply these rational coefficients. Here, everything was integer, only coefficients were integer. Okay, now why did that work? So solving one linear equation for a given variable and then plugging that into another linear equation is the same as adding a multiple of the first equation to the second, right? Because if you think about it, it sounds a bit obvious, but well, as you'll see soon, it will give a new perspective on how you handle these equations. Now, that last fact here is only true for linear equations, and that's really important, right? So I hope that's clear, right? So try to take, quadratic equation or cubic equation, do a substitution or do the addition, you're gonna have something completely different. So that's another, if you like, that's why linear algebra works, right? So because of this statement is true. So what did we do eventually? So we solved the system of linear equations by transforming them into simpler but equivalent, i.e. having the same set of solutions form. Right, so all of those transformations, subtractions and additions of equations with coefficients, they did not change the space of solutions of the equation. So we will call them elementary equivalences by adding a multiple of one equation to another and by multiplying equation by a non-zero number. Right, so because they're linear equations, and linear means that the coefficients that do not depend on the variables, these are legitimate elementary operations. And of course, we can also reorder equations, right? It doesn't really matter eventually for the set of solutions, which way you write those equations down. Okay, now, so a new term, augmented matrix. Now, let's abbreviate the system like this. So this is a table, which is called augmented matrix. And the adjective augmented corresponds to adding the column of the right-hand sides of these equations to the right of the table. So this in the left side of the table, you put coefficients of the in front of x, y, and z. in this order. So here order is important. So we have 1, 2, 3, 1, -1, 1, 2, 3, 4. You write them in this table. It's called a matrix. And this matrix we call augmented because we also include the right-hand side, the column of the right-hand side. Okay. So it has as many rows as equations and one more column than the number of unknowns. It's for the, like I said, for the right-hand side. Okay, so that's augmented matrix. Now, let's rewind what we did using this new terminology, new object, augmented matrix. So this is the initial augmented matrix, which corresponded to the system that we had. Now, our operations, so remember what we did, right? So we added the here, yeah. So we added the, we multiplied the second row by -1 and added to the first row. Then you multiply it by -2 and add it to the third row, right? So the second row stays the same, and the first row becomes 0, 3, 2, 5, right? And then the last row becomes 0, 5, 2, 7. Okay, yes, stop me if you guys need more time to process that. Okay, on the next step, okay, maybe somebody tell me, what did we do on the next step? So what happened from this matrix to this matrix? If you remember what we did, so what happened on the second step?
Subtract the first from the third.
First or second?
First from
third. First, yeah, that's right. Yeah, good. Right. So you have 5 minus 3. Yeah, so that's how good. So you have 5 minus 3 is equal to 2, 2 minus 2 is equal to 0, 7 minus 5 is equal to 2, right? And so on. So then we would divide by 2. The third row is divided by 2, and then we would add the third row to the second, right? And then we divide by 2, the first one, right? And finally, we get this equation here. If we, what do we do now? We subtract the first row from the second. So we get this matrix with only one here. And then, of course, it says that z equals 1, x equals 1, and y is equal to 1. Now, this procedure is called row reduction. At each stage, we reduce the number of non-zero entries in a matrix by adding multiples of one row to another. It's called either row reduction or Gaussian elimination. So this is Carl Gauss, famous mathematician. But sort of part of the joke here that if you look at ancient texts, right? So you can find that the idea was there before. Can somebody see what's written here? What is this text about? It must be traditional Chinese, right? Okay, you can tell me later what is written here. Okay, yeah. So this is row reduction. Okay, so let's try it. Okay, we have some time, so let's do it. For which numerical values of s? So here s is a parameter. It's a coefficient in the system. These two systems here, x plus sy equals 0 and minus x plus y equals s plus 1, and x minus y equals 0 are equivalent. S equals -1, Archish, folks, do you agree? Yeah, so if you plug in x equals -1, first equation becomes x minus y equals 0, and second equation becomes minus x plus y equals 0, which is the same thing. Yeah, so that should be correct. Now, but let's sort of verify this using the row reduction. So we'll write down the augmented matrix for the system of equations. Let me show you the system again. So its coefficients will be 1s0, -1, 1s plus 1. Here it is, right? Then we would do the adding the first equation to the second one, right? So that's how we get 1s0, 1 plus s plus 1. And then in the second equation, we now, so yeah, if s is equals to -1, right? Then the second equation says 0 equals 0, right? So here we have to, we cannot just divide by s minus 1 because s plus 1, because this it can vanish, right? So when s is equal to -1, the second equation will be 0 equals 0, and the first will be x minus y equals 0. So in this case, it is equivalent to the second system, which is just x minus y is equal to 0. But if it's not, then not, right? So if we say x is equal to, say, -2, then the solution will be different. Yeah, so because if s is not equal to -1, we can divide by s plus 1. This will be the system, which we can, of course, reduce to this one by multiplying the second equation by -s and adding to the first equation, which tells us that x equals -s and y is equal to 1. And this is not equivalent to the second system, which has solutions s and -s for any value of s. Okay. So this parametric system can have two different sort of branches of solutions. In one case, there are infinitely many solutions, and in the other case, there is a unique solution. Yeah, and the two systems from the previous slide are equivalent if and only if s is equal to -1. Okay, so that's the end of the first first part. So in the next video, we'll continue to refine our solution method. We'll by transforming the given linear system into equivalent but sort of easier to solve shape, and this will be called an echelon form. So we'll consider various reformulations and interpretations for those linear equations. Good. So there'll be another chunk. We can do the following. We can either talk about this right now, or we can stop and then I'll record it and then you can watch it later and we can talk during discussions in office hours. So do you guys want to continue with the echelon form, or shall we take a break? What do you think? I may not have enough time, right? So it should end at 12. I think it's a long. It may go over an hour, sort of. Okay, is anybody here who wants to continue with this with the echelon form? Okay, so if not, then we'll just we'll stop here. So I'll record this video later today, and I upload everything to B courses and to the webpage. Wait, any other questions? Yeah, so feel free to send questions over email, and then so I'll update I'll make an announcement with the updated office hours and discussions. Okay. Thank you, guys. It was nice to meet you all. So I hope we'll have a productive semester. See you later. Bye.